Hello and welcome to our short tutorial about fastMONAI. So in this tutorial we are going to go through how to use the library, and to do this we will use the tutorial for classification notebook that we have made available. And you can run this tutorial in two different ways. So you can either go to fastmonai.no and go down to the section Getting Started. And in there we have a couple of tutorials, and the one we are going to look at is this tutorial for classification. And we have made these tutorials available as Colab notebooks as well. So you can click on that one and just start to run this. And the first cell is just to install fastMONAI. A second option is to go to our GitHub repository, fastMONAI, and clone the project. And pip install it, and then go find the notebook for tutorial for classification. And I would recommend you to make a copy of this notebook before starting. So then I think we are ready to start. So this first cell, as I explained a few minutes ago, this is just for the Colab to install fastMONAI. Otherwise, as I'm running this locally, it will just show that I'm running locally. Okay, so this tutorial is divided into two sections, beginner part and one advanced part. So let's start with this beginner part. So here we start with this cell, which imports all of the functions and classes from the fastMONAI library. And the second part there now is that to demonstrate the use of fastMONAI, we will download the nodule amnist 3D dataset from the medamnist version 2, dataset containing long nodules with labels indicating whether the nodules are benign or malignant. And we do that with using this function from fastMONAI. And yeah, defining that we want the nodule amnist 3D dataset. And you can actually download other datasets as well from medamnist, like this fracture amnist, vessel amnist, and the others. So I will just run this and it will return a data frame. And I've already downloaded these data, so that's why it went so quite fast here now. So the next part will be to look at the data frame we get back, and that is this one. So it will give a data frame with 3 columns, one for the image path, so each image path for each images, and the labels, the values for them, 0 and 1, and whether they are for training or validation. So that's the column isval for. So the next part here is that we are having a list here with all the transformations that we want to use from Torch.io. So we are using SAT normalization, padding or cropping all images to 28 times 28 times 28, and we are using this random affine with degrees 35, which means that we want to rotate the images between plus minus 35 degrees. And if you want to look into additional transformations, you can have a look at our documentation. So we can just run this one. And the next part we will use med image data loaders, which is a high-level API for loading data, and here directly from data frame. So we are just giving in the data frame that we downloaded, with defining where to find the images, which is this image path right, and where to find the labels, the label column. So that's the labels, and how to split the data. So that will be with this isval. So based on the split of medamnist, yeah, and we are also defining the transformations, which is this one. And here we define that all images should be resampled to 1 times 1 times 1 voxel size, although these images are already resampled to this size. So in the background nothing would happen, but this is just to show what's possible if you're using your own data. And we are defining here a batch size of 64. You can just change this value as well, and this highly depends on the memory you have available on your GPU. Okay, so we run this, and now we can have a look at the training data with this show batch in the data loader. You can just change the value to look at more images, and also in the various anatomical plane, as we can see here. Let's change that back again. Okay, so now we are ready to create an object of a model, and we do this with importing MONAI's classifier. And here we are defining the input shape of the images, as I said, 28 times 28 times 28, and the number of classes, 2. And the channels, this one you can play around with as well. And now we are ready to create a learner, which is a fastAI object that combines the data and or define model for training. And in here we are also defining that the metrics that we want to look at during training is this accuracy. So we'll just define this one. And now we are actually ready to do the training, and here we will use this fit one cycle policy in fastMONAI to in fastAI actually to do the training here. So this will take a couple of seconds here, and that also depends on your computer and the computational power you have available. Okay, so now the training is done, and we can have a look at some results on the validation data. And here as well you can play around and change the value. And here we found one that should be 1 but were predicted as 0, so we can have further look at the model's performance, and we can do that with this class interpretation from learner. So we first create an object of this, and from this one we can plot the confusion matrix. And when we plot the confusion matrix, we can see that we are facing class imbalance, which is quite common in medical data sets. So when dealing with a classification task on such imbalanced data sets, specific sampling techniques may be necessary, and we will have a look at that later in this tutorial in the advanced section. But let's continue. We can look at the most confused images with this one, and here as well you can play around. So and that's it for the beginner part, and from here we will have a look at the more advanced part of the library. And we start off with importing only the needed components for our classification task. And here we are doing the same as we did earlier with downloading the data, but this time we are just defining the data frame to be for train and val, and the second part with that we didn't get in the beginner part is the test data frame that we will use this time. So we'll just get those, and this first data frame, the data frame for training and validation, is the same. And we have also a method or a class called med dataset, where you can give a list of your images to get more information about your dataset. So we'll just run this, and from here it will take a couple of seconds to minutes, depends on the size of your dataset and so on. So here we get back the information about the dataset, that the dimensions are 28 times 28 times 28, and the voxel size is 1, and the orientation, and also an example image that you can look at. So all the images here are similar, but in real clinical settings, in real clinical datasets, this can be different from images to images. So that's why we have this class to analyze the data that you're going to use. And here you can also get a suggestion for the resample voxel size, and if the data should be reordered. And further, you can get suggestion for the size for your dataset that we can use here. That's the input shape, and here we have defined the batch size. As I said earlier in this tutorial, The batch size depends on your GPU, the memory you have available there. So I will just put it to 64 here. We can continue running this. I see that I haven't run this part, so I will just run that. And the transformation is similar as we saw earlier. And now here we are using med data block, which is a lower level class than what we did earlier. So here we can define the blocks we want to use, like the category block, which is specific for this task. For segmentation task or regression, they will be different. Otherwise, this splitter is the same. Isval, call reader, where to find the images, where to find the labels, and the transformations, and those things are similar. So we'll just run this one, and we will create a data loader with or data frame for training and validation and defining the batch size. And here I will also show how many data we have for training and how many of those are for validation. So that's the same as the data we used earlier. So here we will just have a show batch to show the images again before defining the model. And yeah, now we are in this part of choosing a loss function, and we are going back to this class imbalance problem that we talked about earlier. So we can see here the labels, that the class 0 is 986, while class 1 is only 337. So there are multiple ways to deal with class imbalance, and I've linked to a page where you can read more about this. So a straightforward technique is to use balancing weights in the model's loss function. And that's what we are going to do here. So we get back the weights for the class weights, and we can just put that into our cross entropy loss. And yeah, and we can give that loss function in now to our learner object. Otherwise, it's similar as earlier. And here we can also now have a summary of our model and see how many parameters that we have available and how many of them are for that are trainable and non-trainable. And here all of them are trainable. Yeah. And from there, now we can use this learn underscore find to find an optimal learning rate. And this can take a couple of seconds here, since it's a small data set. In other cases, it can take longer time. So here we get a suggested learning rate that we will use for the training. So this will be the same policy as we used earlier, fit one cycle from fastAI. So we'll do the training now. And now we can look at the results, and we see that some of them are, yeah, it's missing on some of them. So you can have a further look into how the model performs by going back and getting this class interpretation as we used here, and look at the confusion matrix and compare them to see how the performance is different now. So we will just store the weights now and continue. Let's say that we are happy with our model. So the next part will be to just load our model back again, and now we want to predict on our test data, the test data frame. So we'll just give that in, and then we make a prediction on that one, and let's see how it performs. So we get 0.81, and then we can do test time augmentation, which is a technique where you apply data augmentation when making predictions to produce an average output. So this can yield better performance. In addition, it can provide some measures of its robustness and sensitivities to the augmentation. So we'll just run this, and the default is that it will run it 4 times plus the original prediction. We can see that the performance increases a bit. So when we are done this and we are happy with the model, we can store the variables and export it to be able to make an application, for example, with the learner. Okay, so that's it for this tutorial. So if you're interested in looking into other tutorials. You can look at the regression tutorial and the binary segmentation tutorial, for example. So I will just open this one directly in Notebook Viewer to just have a quick glimpse on this one. So here we are using this Decathlon dataset, the task 2 for hearts, and you can play around with that one. And here we can see in that med data block that we are using med mask block instead of category block that we used earlier. And yeah, I think that's it. So I would say, yeah, thank you.